the universe should not be this quiet. The Milky Way contains hundreds of billions of stars. Many are surrounded by planets, and many formed long before Earth existed. NASA's archive now contains more than 6,000 confirmed worlds beyond our solar system, but those discoveries represent only the planets our instruments have been able to find. The true number in the galaxy is expected to be vastly larger. Rocky planets are no longer considered unusual. Water exists in comets, icy moons, and clouds between the stars. Astronomers have also found carbon-rich molecules in meteorites and in enormous regions of gas and dust where new planetary systems are forming. None of this proves that life begins easily. It does show that the raw materials and possible locations are spread throughout space. With so many opportunities, and with billions of years available, intelligence might have appeared somewhere else long before humans began looking upward. Even one civilization that learned to travel between nearby stars could have left evidence behind. We might expect a radio beacon, a repeating laser pulse, an artificial probe, unusual structures collecting the energy of a star, or chemicals in a distant atmosphere that nature would struggle to produce. So far, no example of any of these has been confirmed. By the end of tonight, you are going to understand what humanity has actually searched, what the silence can and cannot tell us, and why nearly every serious explanation leads to a troubling consequence. Life may be extraordinarily difficult to begin. Complex intelligence may be a rare accident. Civilizations may appear at different times and miss one another completely. Some may become quiet before anyone can hear them. Others may never survive long enough to spread beyond their home world. Before we continue, if you enjoy calm journeys through the largest questions in space, you can like the video and subscribe. It helps this channel continue making long documentaries for nights like this. The silence we are discussing has a precise meaning. It does not mean that astronomers have examined every planet and found it empty. We cannot yet see the surfaces of Earth-sized worlds across most interstellar distances. We cannot monitor every star continuously, listen to every radio frequency, or recognize every form that unfamiliar technology might take. A message could pass Earth while our telescopes are pointed elsewhere. A transmitter could be too weak, too brief, too distant, or aimed in another direction. A civilization could communicate through a method we have not invented. Our search has covered only a small part of an enormous range of possibilities. Even so, the missing evidence matters. Radio telescopes have examined nearby stars across millions of frequency channels. Optical instruments have searched for brief laser flashes. Infrared surveys have looked for the heat that enormous technological systems might release. Spacecraft have photographed planets, moons, asteroids, and the outer regions of our own system. These searches have revealed remarkable natural objects and processes, but no confirmed technological trace from another civilization. That absence can be interpreted in several ways, and the possibilities do not all point in the same direction. Perhaps there is almost no one to find. Perhaps the galaxy contains life that never becomes complex enough to build machines. Technological societies might exist while remaining detectable for only a few centuries. They may communicate in narrow beams, turn inward toward compact forms of existence, or remain hidden by choice. Humanity may also have begun searching far too recently, with instruments that are still too limited to detect what is already there. The frightening part is not that one of these ideas has been proven. None of them has. The frightening part is that each surviving explanation changes the meaning of the silence. If life almost never begins, Earth may be far more unusual than we understand. If intelligence is common but short-lived, the quiet sky may contain a warning about the future of technological species. If civilizations remain hidden, then silence may be something they learned to preserve. If distance and timing keep every society isolated, the galaxy could contain many minds that never learn of one another. To understand which possibilities deserve serious attention, we have to begin with the part of the mystery that makes the silence hardest to dismiss. The Milky Way did not begin when Earth formed. It had already existed for billions of years, producing stars, planets, and possible homes for life, long before our world appeared. By the time Earth began to form, the Milky Way had already been changing for about 9 billion years. The universe itself is approximately 13.8 billion years old. Our galaxy began taking shape roughly 13.6 billion years ago, when enormous clouds of hydrogen and helium started collapsing under gravity. Some of the Milky Way's oldest known stars formed during this early period, while the galaxy was still assembling from smaller clouds and young stellar systems. Earth arrived much later. The solar system formed about 4.57 billion years ago from a rotating cloud of gas and dust. Most of that material gathered at the center to form our star. The remaining matter flattened into a broad disk where grains collided, stuck together, and gradually built the planets, moons, asteroids, and comets. That material had a long history before it reached our neighborhood. The first stars formed mainly from hydrogen and helium, the two lightest elements. They contained almost none of the carbon needed for organic chemistry, the oxygen found in water, the silicon that forms much of a rocky planet's crust, or the iron that collects inside planetary cores. Astronomers call elements heavier than hydrogen and helium metals, even when those elements would not normally be described as metals on Earth. Stars manufactured many of these heavier elements through nuclear fusion. Deep inside a star, enormous pressure forces lighter atomic nuclei together and produces heavier ones. Massive stars can continue this process until elements near iron are created in their cores. When some massive stars reach the ends of their lives, they explode as supernovae. These explosions throw newly formed material across interstellar space. Other elements escape through stellar winds, while some of the heaviest are produced when neutron stars collide. A neutron star is the extremely dense collapsed core left behind after certain massive stars explode. New stars eventually form from clouds enriched by the remains of older stars. Their planets inherit the same material. Astronomers call this gradual buildup galactic chemical evolution. Each generation changes the ingredients available to the generations that follow. The earliest period of the Milky Way may therefore have offered fewer opportunities for rocky, chemically complex worlds. Conditions improved as stars completed their lives and returned newly formed elements to space. By the time our solar system appeared, several generations had already enriched the galaxy. Some rocky planets may be much older than Earth, while still containing abundant carbon, oxygen, silicon, and iron. The exact age range remains uncertain, because astronomers cannot date most exoplanets with the precision available for objects in our own system. Even so, confirmed planetary systems exist around stars several billion years older than ours. A world that formed 2 billion years before Earth would have received 2 billion additional years for oceans to settle, climates to stabilize, chemistry to develop, and evolution to proceed. A 4 billion year head start is almost as long as the entire history of life on our planet. Recorded human history covers only several thousand years. 1 billion years contains that span well over 100,000 times. A civilization could spend millions of years developing technology during such a head start. Vast stretches of time would still remain before the first humans appeared. Biology elsewhere would not need to follow Earth's timetable. Life might begin later, progress more slowly, remain microbial, or never appear at all. The importance of the head start comes from the number of opportunities. Across hundreds of billions of stars, some worlds may have begun their biological histories far earlier than ours. If even one of those older worlds produced a civilization capable of surviving for a small fraction of its planet's history, its machines and signals could predate every human invention by millions or billions of years. A civilization with that much time would not need to break the speed limit of light. Patient travel between nearby stars, repeated often enough, could leave evidence across much of the galaxy. The Milky Way stretches for more than 100,000 light-years from one side of its stellar disk to the other. That scale sounds like a permanent barrier, especially when the nearest star system is already about 4.24 light-years away. Yet, neighboring stars are usually separated by distances of only a few light-years, and a journey does not have to cross the entire galaxy in one attempt. Imagine a spacecraft moving at 1% of the speed of light. That is far beyond anything humans have built, though it remains comfortably below the limit set by relativity. At that speed, a voyage of 4 light-years would take about 400 years. A trip of 10 light-years would require roughly 1,000 years. Those durations are enormous beside a human lifetime. They become much smaller when placed inside a history measured in millions of years. Suppose one inhabited system sends missions towards several nearby stars. Some destinations may prove unsuitable, while others may contain asteroids, moons, or planets with useful raw materials. A successful settlement could spend centuries building habitats and developing its own spacecraft. Once ready, it could send missions toward additional stars. The process would spread as a branching network. Each established system becomes a new point of departure, so the original world does not need to launch every mission itself. One settled system might lead to 2 more. Those destinations could later produce 4 additional branches, followed by a wider wave moving through the galactic disk. The exact growth would never remain perfectly regular. Stars move around the galaxy. Settlement attempts could fail. Civilizations might pause expansion for long periods, or choose only certain destinations. Even with these delays, repeated branching can cover territory far faster than a single vessel following one continuous route. Researchers have built computer models to explore different versions of this process. The results vary because the assumptions vary. Faster ships, short construction periods, and frequent launches can produce expansion across much of the Milky Way in a few million to a few tens of millions of years. Slower migration, selective settlement, and long pauses can stretch the process across hundreds of millions of years. Some cautious models allow it to continue for billions. Every one of those timescales fits inside the history available to planetary systems older than ours. A separate idea replaces settlers with machines. In 1966, the Hungarian-born mathematician John von Neumann's work on self-reproducing automata inspired later discussions of robotic probes that could copy themselves. These are now commonly called von Neumann probes, although he did not design an interstellar spacecraft. A probe of this kind would arrive in a new system and search for metals, carbon, silicon, and other materials in asteroids or small moons. Automated factories would process those resources into replacement parts and new spacecraft. The copies would then depart for different stars, while the original probe continued observing or manufacturing. No machine with this ability exists today. Building one would require reliable autonomous mining, manufacturing, navigation, and repair across centuries without human assistance. A copying error could disable later generations, and uncontrolled replication would create serious risks. The concept still matters because it shows how exploration could continue without transporting biological passengers or maintaining a continuous political empire. Even modest speed becomes powerful when machines can reproduce at each destination. At 1% of light speed, travel between nearby stars may take centuries. If a probe then spends another few hundred years building copies, each step might require roughly 1,000 years. 10,000 such steps would fit inside 10 million years, while thousands of branches could be operating at the same time. The Milky Way's size remains extraordinary. Its age is even more important. A wave that needed 100 million years would consume less than 1% of the galaxy's lifetime. A process lasting 1 billion years could have finished several times during the head start available to some older planetary systems. That does not show that any civilization has expanded this way. It shows that ordinary travel speeds and repeated branching leave enough time for the possibility. If such a wave ever crossed our region, its traces might include abandoned probes, altered star systems, artificial energy use, or settlements that continued long after the original civilization changed. The apparent absence of those traces turns a calculation about travel into the simple mystery that Enrico Fermi expressed over lunch. That contradiction entered scientific history during the summer of 1950 at the Los Alamos Laboratory in New Mexico. Physicist Enrico Fermi was walking to lunch with several colleagues, including Edward Teller, Emil Konopinski, and Herbert York. Their conversation moved through recent newspaper stories about flying saucers and then toward the possibility of travel between stars. A cartoon in the New Yorker had jokingly blamed missing public trash cans on visiting aliens, which gave the group one more reason to talk about extraterrestrial life. Accounts of the lunch were written down years later, so some details differ between witnesses. The remembered moment is remarkably consistent. In the middle of the discussion, Fermi suddenly asked, "Where is everybody?" He did not publish a paper presenting a formal Fermi paradox. The name came later, as other researchers developed the reasoning behind his short question. The galaxy contains an enormous number of stars. Many are older than our solar system. Travel between neighboring systems appears physically possible at speeds below that of light, and repeated settlement could spread over immense distances during a small fraction of galactic history. Yet Earth shows no accepted evidence that such an expansion has reached this region. No confirmed alien probe has been recovered. Astronomers have identified no engineered star system and received no verified transmission from another civilization. The expectation points toward visible activity, while observation continues to show natural planets, natural stars, and unexplained events that never become proof. The word paradox can make this sound like a logical impossibility. Scientists use it more loosely here. The Fermi paradox is a conflict between a set of plausible assumptions and the evidence currently available. Resolving it requires at least one assumption to change. Perhaps suitable planets are less common than they appear. Life may begin only under unusual chemical conditions. Complex cells could require a rare evolutionary event, Intelligence might emerge frequently without producing technology. A civilization may also remain detectable for such a short period that two societies almost never overlap. Frank Drake gave these possibilities a more organized form 11 years after Fermi's lunch. In November of 1961, 10 researchers gathered at the National Radio Astronomy Observatory in Green Bank, West Virginia. The meeting was one of the first scientific conferences devoted specifically to the search for intelligent life beyond Earth. Drake needed a practical way to arrange the discussion, so he wrote an equation containing 7 factors. It begins with the rate at which stars form in the Milky Way. That value is combined with the fraction of stars that possess planets. The next factor estimates how many worlds in each planetary system might provide conditions suitable for life. From there, the equation enters territory that remains far less certain. It asks how often life actually begins on a suitable world, how often that life develops intelligence, and how often an intelligent species creates technology that can be detected across space. The final factor is the average length of time that a civilization remains detectable. Each factor is multiplied by the others. This matters because one very small value can reduce the final result sharply. A galaxy may produce many habitable planets, while a tiny probability for the origin of life leaves almost all of them sterile. Intelligence could be common, while an average detectable lifetime of only a few decades produces very little overlap. The final lifetime term is especially powerful. Suppose new technological civilizations appear at a steady rate, but each broadcasts recognizable signals for only 100 years. Very few may be active at the same moment. Extend that lifetime to 1 million years, and the number present together rises enormously without changing any of the biological terms. Astronomy has made progress on the opening parts of Drake's equation. Researchers now know that planets are common, including small rocky worlds. Measurements of exoplanet atmospheres and orbits continue to improve. The later factors still rest on a sample of one inhabited planet and one technological species. Earth confirms that the full sequence can occur. It does not reveal how often each step succeeds elsewhere. The Drake equation therefore provides a map of the uncertainty. The silence may begin with planet formation, continue through biology, or appear only after technology develops. Determining where the missing civilizations went first requires understanding how much of the sky humanity has truly examined. That map of uncertainty became a real experiment in the spring of 1960 in the wooded hills of Green Bank, West Virginia. Frank Drake was 29 years old and working at the National Radio Astronomy Observatory. He had recently become interested in a practical idea that had once belonged mostly to speculation. If another civilization used radio technology, its transmissions might cross interstellar space and arrive at Earth as a measurable signal. Drake used the Howard E. Tatel radio telescope, an 85-foot dish completed only a short time earlier. The telescope stood in a valley, protected from much of the radio noise produced by cities. Its metal surface collected faint radio waves and focused them into a receiver, much as an optical telescope gathers visible light. The experiment was called Project Ozma, after the princess in the Land of Oz stories. Drake selected 2 nearby stars, Tau Ceti and Epsilon Eridani. Both are visible without a telescope under dark skies, and both lie roughly 11 light-years from Earth. Their distances meant that any signal received in 1960 would have left its source around 1949. The 2 stars also appeared reasonably similar to our own star by the standards of the time. Tau Ceti is a quiet yellow star, slightly smaller and cooler than ours. Epsilon Eridani is a younger orange star with stronger magnetic activity. Astronomers did not yet know whether either star possessed planets. The first confirmed planets around ordinary stars would not be announced until 1995. Drake tuned the receiver near a frequency of 1,420 MHz. This corresponds to radio emission from neutral hydrogen, the simplest and most abundant element in the universe. Hydrogen atoms naturally emit radio energy at a wavelength of about 21 centimeters when the orientation of an electron changes relative to the proton in the atom. A scientifically capable species might recognize that frequency as a universal landmark. The idea did not require two civilizations to share a language or a calendar. Both could measure the properties of hydrogen. Project Ozma searched for signals concentrated inside an extremely narrow frequency range. Many natural radio sources spread energy across broad bands. A transmitter designed for communication can place much of its power into a narrow channel, making it stand out against the surrounding noise. The receiver examined one channel only about 100 Hz wide at a time. 100 Hz is a tiny slice of the radio spectrum. Modern searches can process millions or billions of channels at once, but Drake's equipment relied on analog electronics, a paper chart recorder, and a loudspeaker. He watched a pen trace the changing signal strength while listening for tones that did not resemble ordinary cosmic static. During an early observation of Epsilon Eridani, a strong signal suddenly appeared. It was exciting enough that Drake quickly pointed the telescope away from the star. The signal remained. That behavior showed that it was coming from somewhere near Earth rather than from the distant system. The most likely source was radar from an aircraft passing through the region. That false alarm revealed a difficulty that still shapes the search today. Human technology fills parts of the radio spectrum with television carriers, navigation systems, satellites, radar, and communications equipment. A distant signal must be separated from all of them. Project Ozma observed the two stars for about 150 hours over several months. It found no confirmed extraterrestrial transmission. The result placed no meaningful limit on the rest of the galaxy. Only two targets had been examined, through one narrow portion of the spectrum, during a very small number of hours. Even so, the experiment changed the subject permanently. A question discussed over lunch had become something that could be tested with instruments. Humanity had begun listening, although the opening was barely wider than a keyhole. 17 years later, a different radio telescope recorded a narrow signal that lasted 72 seconds and seemed to arrive from the sky. On August 15, 1977, the Big Ear radio telescope was scanning a narrow strip of sky above Ohio. Big Ear belonged to Ohio State University and stood near the city of Delaware, about 30 miles north of Columbus. Unlike a dish that could turn toward different targets, its large reflecting surfaces remained fixed. Earth's rotation carried different parts of the sky through the telescope's receiving beam. The instrument recorded its measurements continuously, printing rows of letters and numbers onto paper. Each character represented the strength of radio energy measured during a 12-second interval. Low values appeared as numbers. Stronger readings were represented by letters farther along the alphabet. Several days after the observation, volunteer astronomer Jerry Ehrman examined the printout. One short sequence stood apart from the surrounding background. It read, 6EQUJ5. Ehrman circled the characters in red ink and wrote a single word beside them. Wow! The name remained attached to the event. The sequence described a signal that grew stronger as its apparent source entered the telescope's beam, reached a peak, and then faded as Earth's rotation carried the beam beyond it. The entire rise and fall lasted 72 seconds, which was the maximum length of time a fixed point in the sky could remain inside Big Ear's observing pattern. That timing gave the signal one of its most interesting properties. A burst of interference produced near the telescope could appear and disappear in many ways. This event followed a shape broadly consistent with a distant, stationary radio source moving through the beam because the planet beneath the telescope was turning. The signal was also narrowband. Its energy was concentrated inside one radio channel roughly 10 kHz wide. Many natural objects produce radio energy across much broader ranges. A narrow signal can therefore resemble the output of a transmitter designed to place energy at one carefully selected frequency. Its frequency lay close to the neutral hydrogen line near 1420 MHz, the same region that had interested Frank Drake during Project Ozma. Hydrogen is the most abundant element in the universe, giving that part of the spectrum an obvious scientific significance. The observation still contained serious limitations. Big Ear used two separate receiving beams that crossed the same area of sky a few minutes apart. The signal appeared in only one of them. Researchers could not determine whether it had switched off before the second beam arrived, changed frequency, or originated from interference that happened to imitate a celestial source. The telescope returned to the same region repeatedly. Later searches used Big Ear and other radio observatories, sometimes covering wider frequency ranges with more sensitive equipment. The signal never appeared again. That missing repetition prevented astronomers from measuring it with another instrument. They could not refine its exact position enough to identify a particular star, planet, or natural radio source. The printed characters contained no message to decode. They recorded signal strength over time and nothing more. Several explanations have been proposed over the decades. Terrestrial interference remains possible, although no specific transmitter was confirmed. Reflections from aircraft or space hardware have also been considered. Natural hydrogen emission has been suggested, including a later proposal involving comets, but those ideas have not produced a widely accepted solution. The wow signal therefore remains unexplained. That word carries a precise scientific meaning. Available evidence has not established its source. The same evidence also falls far short of demonstrating extraterrestrial technology. A dependable detection would need to repeat or continue long enough for independent observatories to locate it. Researchers would compare measurements from widely separated telescopes, check whether the signal moved with the sky, examine its frequency drift, and rule out satellites or equipment near Earth. A pattern carrying recognizable information would strengthen the case further. The 72 seconds recorded by Big Ear supplied none of those later steps. Possibility appeared briefly in a paper record and disappeared before astronomy could test it properly. Future searches would need to monitor more stars, revisit promising signals, and process enough data to separate rare celestial events from the constant radioactivity surrounding Earth. By the 1990s, radio astronomy had moved far beyond the single narrow channel used during Project Ozma. Project Phoenix operated from 1995 until 2004. Its teams used major observatories in Australia, Puerto Rico, and West Virginia to examine about 800 nearby stars. Instead of waiting for unusual radio energy to appear anywhere in the sky, the project concentrated on individual stellar systems within roughly 240 light-years. For each target, its equipment covered more than 1 billion frequency channels. That represented an enormous technical advance over Frank Drake's original receiver, though the observations still depended on borrowing time from telescopes built mainly for other kinds of astronomy. The Allen Telescope Array later offered a more dedicated approach. Its 42 radio dishes stand at Hat Creek Observatory in Northern California. Computers combine the signals collected by the separate antennas, allowing the array to behave like a larger observing system and examine several regions of the sky more efficiently. A much larger change began in July of 2015 with Breakthrough Listen. The project brought together radio telescopes, optical instruments, and powerful computing systems designed to process quantities of data that earlier researchers could not have stored. One of its major nearby star studies used the Robert C. Byrd Green Bank Telescope in West Virginia and the Parkes Radio Telescope in New South Wales, Australia. Green Bank's movable dish is 100 meters across. The Parkes dish measures 64 meters across and has taken part in radio astronomy since 1961. Between January of 2016 and March of 2019, the two observatories examined 1,327 nearby stars. Green Bank observed 1,138 of them. Parkes covered the remaining 189. The search extended from approximately 1.1 to 3.45 gigahertz. A gigahertz represents 1 billion radio wave cycles each second. That frequency range contained billions of narrow channels where a concentrated artificial transmission might appear. The processing system also searched for Doppler drift. Doppler drift is a slow change in a signal's measured frequency caused by motion. The effect is similar to the changing pitch of a passing siren. A transmitter placed on the surface of a rotating planet would move toward Earth during part of each rotation and away during another part. Its planet would also travel around its star, adding another layer of motion. From Earth, those movements could make a narrow transmission slide gradually across the radio spectrum. A signal produced by nearby electronic equipment may remain fixed at one frequency, while a signal arriving from another moving world could drift by a measurable amount each second. The Breakthrough Listen analysis searched drift rates from approximately -4 to +4 Hz per second. Software identified large numbers of events that initially met basic signal requirements. Researchers then compared observations taken while the telescope was aimed at the target with observations made in nearby directions. A genuine signal from a particular star should become strongest when the telescope points toward that star. Many candidates continued appearing when the telescope moved away. That behavior connected them to human radio activity, satellites, or equipment around the observatories. After the events consistent with terrestrial interference were removed, 0 candidates remained. The study produced roughly 219 terabytes of publicly released data. 1 terabyte can hold hundreds of hours of compressed audio, so the complete collection represented a quantity that would have been difficult to imagine during Project Ozma. The null result still had a defined boundary. For some targets, Green Bank could have detected a continuously operating narrowband transmitter with an effective power near 2 trillion watts. The Parkes observations generally required stronger transmissions, closer to 9 trillion watts. These values describe how powerful a source would appear if its energy were radiated equally in every direction. A focused beam aimed directly at Earth could be detected with less total power. A transmitter aimed elsewhere could remain invisible regardless of its strength. Brief signals might arrive between observations, while weak leakage could disappear beneath natural radio noise. The survey therefore made nearby civilizations with loud, persistent transmitters less likely within the frequencies examined. It left quiet societies, intermittent beacons, tightly directed communications, and unfamiliar technologies largely untouched. The search had become enormous by human standards. The complete range of possible extraterrestrial signals was larger still. 1,327 stars sounds like a broad search until those observations are placed inside the full problem. A radio telescope must begin with the correct part of the sky. The Milky Way contains hundreds of billions of stars, and each target occupies only a tiny angle above Earth. Even when an observatory points toward the right system, the receiver must also cover the frequency being used. Frequency describes how many times a radio wave repeats each second. Human technology operates across a huge range, from low-frequency navigation signals to radar and satellite communication measured in billions of cycles per second. An extraterrestrial transmitter could use any part of that spectrum where radio waves can travel through its atmosphere and the space between stars. Bandwidth adds another dimension. A narrowband beacon may concentrate its energy inside only a few hertz, while a complex communication signal could occupy thousands or millions of hertz. Search software designed for one type may overlook the other. Radio waves can also have different polarization. This describes the direction in which the wave's electric field moves. A receiver that records the wrong polarization may detect only part of the signal's strength. Distance and transmitter power determine whether the signal rises above background noise. Repetition rate and duration decide whether it is present during an observation. Frequency drift changes where it appears as planets rotate and orbit. Altogether, the search depends on position, frequency, bandwidth, polarization, strength, timing, duration, repetition, and motion. Researchers sometimes describe this enormous set of possibilities as the cosmic haystack. The desired signal is the needle, while every combination of sky position and technical property forms another part of the hay. A transmitter could sit inside a star system that has already been observed and still remain undetected. Its beacon may operate for 10 minutes, once every year. A telescope that watched for 5 minutes on a different date would record silence. The signal might also fall just beyond the frequencies covered by the receiver or arrive below its sensitivity limit. In 2018, researchers estimated how much of this multi-dimensional haystack previous radio searches had examined. Depending on the assumptions used, the fraction resembled the amount of water in a large hot tub or a small swimming pool, compared with all the water in Earth's oceans. The comparison does not erase the value of earlier surveys. Searching one pool-sized portion can rule out certain signals within it. It also shows why decades of null results have not settled whether technological life exists elsewhere. Distance makes weak transmissions especially difficult to detect because radio energy usually spreads outward as it travels. The surface area covered by the wave grows with the square of the distance. This relationship is called the inverse square law. Move twice as far from a transmitter, and the signal reaches the receiver at 1/4 of its former strength. At 10 times the distance, only 1/100th of the intensity remains. A 1,000-fold increase in distance reduces it to 1/1,000,000th. A narrow beam changes the calculation by concentrating energy toward a specific destination. Planetary radar provides a useful human example. Radar facilities send powerful signals toward planets or asteroids and measure the faint reflection that returns. Someone located near the beam's path might detect that concentrated transmission across a much greater distance than ordinary television or radio leakage. Most everyday broadcasts spread more broadly and were designed to reach receivers on or near Earth. Some signals escape into space, creating an expanding region of human-made radio energy. The earliest experiments date to the late 19th century, while regular broadcasting began during the early 20th. Our oldest radio emissions have therefore traveled outward for more than a century. Their travel distance does not guarantee detectability. Ordinary leakage weakens, while mixing with natural radio emission from stars, gas clouds, and the galaxy itself. Detecting it from another system could require a very large instrument aimed toward Earth during the correct transmission. A deliberate beacon would be different. Its designers could select a narrow frequency, use high power, and aim the signal toward a known planet. That choice would make detection much easier, provided a receiver was watching at the right moment. Current null results place the strongest limits on persistent, powerful signals that fall inside well-studied frequency ranges. They say much less about brief transmissions, weak leakage, or beams directed elsewhere. Technologies using optical light, physical probes, or methods unknown to present science would occupy different searches entirely. Radio silence, therefore, describes the region humanity has examined with radio instruments. Large sections of the cosmic haystack remain untouched. Messages can hide through timing and distance. Large technological systems may be harder to conceal because using energy changes the light and heat released into space. A civilization can remain silent and still alter the light around it. In 1960, physicist Freeman Dyson proposed that a very advanced society might collect a large fraction of the energy produced by its star. Popular illustrations often show a solid shell enclosing the entire star, but Dyson's practical idea was closer to a swarm. Millions or billions of independent collectors could occupy separate orbits, gathering light while leaving large gaps between them. Such a project would require extraordinary amounts of material. Mercury alone contains about 330 billion trillion kilograms of rock and metal. A civilization able to dismantle planets or mine large numbers of asteroids could, in principle, turn some of that material into solar collectors, habitats, factories, and communication systems. The important feature for astronomers would be heat. Energy cannot simply disappear after it has been used. Starlight captured by a machine may power computation, manufacturing, transportation, or life support systems. Eventually, much of that energy must leave the equipment as waste heat. A warm object releases most of its energy at longer wavelengths than visible light. Human eyes cannot see these wavelengths, but infrared telescopes can measure them. An incomplete Dyson swarm might therefore make a star look slightly dimmer in visible light and unusually bright in infrared. Dust can produce a similar pattern. Tiny grains around young stars absorb visible light, warm up, and release infrared radiation. Collisions between asteroids can also create dusty clouds. Any proposed megastructure must therefore compete against natural explanations that are already common throughout the galaxy. Astronomers have extended this search from individual stars to entire galaxies. A civilization that used a large fraction of the energy from billions of stars would release an immense amount of heat. The Glimpsing Heat from Alien Technologies survey examined roughly 100,000 galaxies using infrared observations from NASA's Wide Field Infrared Survey Explorer. The survey found no clear galaxy in which technology appeared to be converting most of the available starlight into waste heat. None of the examined systems showed the extreme signature expected if more than roughly 85% of its stellar energy had been captured and re-radiated in the middle portion of the infrared spectrum. That result applies to highly conspicuous galaxy-spanning activity. Smaller civilizations could remain far below the detection limit. A society using the energy of one planet or part of one star system would disappear inside the combined light of billions of ordinary stars when viewed from another galaxy. Project Hephaestus has searched closer to home by comparing optical and infrared measurements of millions of stars. In 2024, researchers reported 7 unusual candidates from a starting sample of about 5 million objects. All 7 were cool red dwarf stars, showing more infrared radiation than expected. The candidates attracted attention because a partial Dyson swarm could produce that kind of excess. Follow-up work soon showed how difficult the interpretation was. A dusty galaxy located far behind a nearby star can appear in nearly the same line of sight. The optical telescope records the star, while an infrared instrument with lower resolution may also collect heat from the distant galaxy. Combining the measurements can make one ordinary star appear unusually warm. Researchers found that this background contamination could explain several of the original candidates and might eventually account for all 7. In 2026, observations with the James Webb Space Telescope examined 2 candidates in greater detail and found distant dusty galaxies contributing the infrared emission. Those 2 objects no longer required a technological explanation. Heat is only one possible technosignature, meaning an observable sign created by technology. Industrial activity could alter a planet's atmosphere by producing gases such as nitrogen dioxide or chlorofluorocarbons. Chlorofluorocarbons are manufactured compounds once widely used in refrigeration on Earth, and some can remain in an atmosphere for decades or longer. Artificial lighting could brighten the night side of a planet. Powerful lasers might appear as brief flashes far brighter than ordinary reflected light. Large orbiting structures could block a star in shapes or patterns that differ from the smooth, repeating dip produced by a planet crossing in front of it. Each method searches for a different physical consequence of technology. None depends on another civilization choosing to introduce itself. The absence of enormous infrared structures therefore carries more weight than a missed radio message. Though it still applies mainly to civilizations using energy on a highly visible scale. Smaller machines would be harder to recognize, especially if they were cold, inactive, or hidden among natural objects. The nearest technological evidence may not surround a distant star. It could be an old probe resting somewhere among the moons, asteroids, and stable orbits of our own solar system. A robotic visitor would not need to announce itself with a radio beacon. In 1960, physicist Ronald Bracewell described a different way for distant civilizations to communicate. Instead of sending repeated signals across light years, they might place an automated probe near another star and allow it to wait. The machine could observe planets, monitor radio activity, and respond only after a local species developed the ability to notice it. Such a probe might remain useful long after its makers changed or disappeared. Electronics would eventually fail, yet a carefully designed object could spend centuries in a quiet orbit before activating. A larger machine might carry repair systems, spare components, or a small factory able to replace damaged parts. This idea connects with the self-replicating probes discussed earlier. Biological travelers require air, food, radiation protection, and a stable habitat. Machines can tolerate longer journeys and remain dormant during most of the trip. After reaching a new system, an advanced probe could mine metal-rich asteroids, refine silicon, and manufacture copies without carrying every kilogram of material from home. No spacecraft has ever demonstrated that complete chain. Human missions reveal parts of it in much simpler form. Japan's Hayabusa 2 collected material from the asteroid Ryugu and returned it to Earth in 2020. NASA's OSIRIS-REx mission brought samples from Bennu 3 years later. Robotic vehicles on Mars can navigate, drill, and analyze rock, while experimental machines on Earth can manufacture components with limited supervision. Turning those abilities into a self-repairing interstellar factory would require a much higher level of reliability. If an older civilization sent probes into our system, several locations could preserve them. The Moon has no rain, oceans, or active plate tectonics. Objects resting on its surface can remain recognizable for long periods, although micrometeorite impacts and radiation gradually damage exposed material. NASA's Lunar Reconnaissance Orbiter has photographed the Moon at resolutions fine enough to show Apollo landing sites, but its cameras have not examined every square meter closely enough to identify every small, unfamiliar object. Near-Earth asteroids offer many hiding places. Most are known only from points of light moving against background stars. Their sizes, rotation rates, and broad compositions can sometimes be estimated from telescopes or radar, while detailed surface maps require a spacecraft encounter. The main asteroid belt contains far more objects than any fleet has visited. Astronomers have catalogued more than 1 million asteroids, and many smaller bodies remain undiscovered. A machine only a few meters across could resemble an ordinary boulder in a distant image, especially after collecting dust or suffering impacts. Stable orbital regions create another possibility. A Lagrange point is a location where the gravity of two large bodies and the motion of an orbiting object balance in a useful way. The Earth and Moon have 5 such regions, and the Earth star system has another 5. Spacecraft can remain near some of these locations with relatively small course corrections. Natural dust and small asteroids can also occupy nearby orbits, making an inactive artifact difficult to recognize from a telescope. These places have not been ignored. Surveys track asteroids that approach Earth. Lunar orbiters map the Moon, and spacecraft have visited selected comets and small worlds. The coverage remains uneven because the solar system contains an enormous volume and millions of potential targets. Most objects have never been seen at close range. No confirmed extraterrestrial artifact has been discovered on the Moon, among the asteroids, near a Lagrange point, or anywhere else in the solar system. Unusual objects have repeatedly received natural explanations once better measurements became available. That absence weakens the simplest version of galactic expansion, where old civilizations send durable machines into nearly every system. It does not exclude a small, inactive probe hidden among natural debris, and it does not show that such probes are practical to build. Their absence may reflect the journey itself. Reaching another star requires a machine to survive energy demands, radiation, dust impacts, navigation errors, and decades or centuries without repair from home. A probe, leaving our solar system, would face its first major difficulty long before reaching another star. It would need to gain enough speed for the journey to finish within a useful span of time. The nearest stellar system is Alpha Centauri. Its closest member, Proxima Centauri, lies about 4.24 light-years away. A light-year is the distance light travels in 1 year, equal to roughly 9.5 trillion kilometers. Even at 10% of light speed, the cruising portion of a voyage to Proxima Centauri would last more than 42 years. Acceleration and braking would add further time. A spacecraft traveling at 1% of light speed would need about 424 years, assuming it could begin and end the trip without slowly changing speed. Human spacecraft remain far below either velocity. Voyager 1 moves through space at roughly 17 kilometers per second relative to our star. 10% of light speed is close to 30,000 kilometers per second, more than 1,700 times faster. Reaching that speed requires an enormous amount of energy. Accelerating a spacecraft with a mass of 1,000 kilograms to 10% of light speed would require approximately 4.53 times 10 to the 17th joules of kinetic energy. That figure represents only the energy contained in the craft's motion. A real propulsion system would lose energy through heat, exhaust, imperfect conversion, and equipment operation. The craft would also need instruments, communication hardware, navigation systems, and protection for its electronics. Any mission expected to stop at its destination would require another way to remove almost the same amount of motion. The mass begins to grow quickly. Adding shielding makes the spacecraft heavier. Accelerating the extra material then demands more energy. A larger propulsion system adds still more mass, while onboard fuel must push both the spacecraft and the remaining fuel that has not yet been used. Chemical rockets handle this problem poorly because their exhaust does not leave the engine fast enough. Carrying enough conventional propellant for an interstellar mission would cause the starting mass to become impractical. Proposed alternatives include nuclear fusion engines and laser-driven sails pushed from the home system. Each remains far beyond any completed spacecraft. The space between stars also contains matter. In some regions, only about 1 hydrogen atom occupies each cubic centimeter. That density feels almost empty, yet a fast spacecraft sweeps through an enormous volume during a journey lasting several light-years. At 10% of light speed, hydrogen atoms strike the front of the craft with enough energy to damage materials and electronics over time. Charged particles can create secondary radiation when they enter shielding. The vessel might need a thick protective layer, a magnetic system that redirects charged particles or material designed to erode gradually while protecting the interior. Dust creates a more concentrated threat. A grain that would seem harmless at ordinary speed carries much greater impact energy when the collision occurs at thousands of kilometers per second. A large particle could puncture shielding or release a cloud of hot fragments. Engineers have proposed placing a sacrificial shield far ahead of the main vehicle. Other concepts use lasers to detect and vaporize approaching grains before impact. Both approaches require reliable equipment operating for decades without maintenance from Earth. Navigation becomes equally demanding. A tiny error in direction grows across trillions of kilometers. The destination star also moves during the voyage, so the craft must aim for where it will be many years later. Course corrections consume energy and must be planned with limited information from home. Arrival creates the final obstacle. A fast probe that does not slow down may cross an interplanetary system in days. Scientific instruments would have little time to observe each world, and communication could continue for years before the collected data returned to Earth. Stopping requires a braking system. The craft might carry additional propellant, deploy a magnetic sail against charged particles, or use light from the destination star. Each method adds uncertainty and equipment to a vehicle already pushed close to engineering limits. Interstellar travel remains compatible with known physics. Its linked problems make expansion less automatic than the simple settlement models suggest. An advanced civilization could possess the necessary knowledge and still decide that centuries of effort, extreme energy use, and fragile machinery offer too little return. Information avoids many of these engineering burdens. A radio wave needs no shielding or fuel once transmitted, and it travels at the speed of light. Contact still depends on two civilizations being detectable during the same narrow period of galactic history. Radio changes the problem from moving matter to moving information. Once a transmission leaves an antenna, it crosses space at the speed of light and requires no fuel for the rest of its journey. The delay remains fixed by distance. Humanity has occupied this technological phase for only a brief period. Heinrich Hertz produced controlled radio waves in the late 1880s. Guglielmo Marconi began practical wireless experiments during the 1890s, and regular commercial broadcasting developed during the early 20th century. Our strongest early transmissions have therefore been traveling through space for roughly 130 years. Systematic listening began even later. Project Ozma observed Tau Ceti and Epsilon Eridani in 1960. The organized search for extraterrestrial intelligence has existed for only several decades inside a galaxy more than 13 billion years old. Consider a civilization located 1,000 light-years away. A signal reaching Earth tonight would show what that society transmitted 1,000 years ago. The information would have begun its journey during the early 11th century, when much of Europe was still organized through feudal kingdoms, and the Song dynasty ruled large parts of China. A reply sent from Earth would need another 1,000 years to reach the same system. The complete exchange would span at least 2,000 years, even before either side took time to interpret the message and prepare a response. The civilization that receives our answer may have changed its language, government, technology, or location. It may also have stopped transmitting long before our message arrives. This delay creates a problem separate from distance. Detection requires two civilizations to overlap during periods when one is producing a recognizable signal and the other is capable of receiving it. Suppose a society uses powerful, broadly detectable radio for 500 years. Another civilization in the same region begins listening 10,000 years later. Both may survive for long periods, yet neither encounters the other's active radio phase. The earlier signals continue moving outward as a thin, expanding shell. Once that shell passes the later world, the opportunity disappears unless more transmissions follow. Researchers sometimes describe the beginning of likely contact as a civilization's contact era. The idea connects the age of a technological society with the volume of space reached by its signals. During the first century, a radiosphere extends only 100 light-years from its source. After 1,000 years, it reaches systems within 1,000 light-years. The number of stars inside that growing volume rises rapidly, although actual detection still depends on transmitter power and receiver sensitivity. Models of this process show that nearby contact may remain improbable for several hundred to several thousand years.